Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2024 paper of Physics Unit 6. Moving on to the first question, we are told that a student investigated the oscillations of a straight spring using this apparatus given over here. Now we are asked that the student gave the mass a small vertical displacement and then released it, and used the stopwatch to determine the time period t of the oscillations. We have to describe how she should determine an accurate value for t. Since this is an oscillation, one of them would be to use a fiducial marker or a timing marker at the center of the oscillation. This is a common point for any type of question regarding the time period of oscillations. And we'll ignore the first few oscillations as well. We'll ignore the first few oscillation. We could also write this point as allowing the oscillations to settle. And the third point would be to calculate, to repeat the experiments or measure the time period over a few oscillations, 10, 5, 20. So those are our 3 points. So this is the first point, this is the second point, this is the third point. Now we are given that the student attaches the spring to a vibration generator. This is the signal generator for this vibration generator. She used the signal generator to vary the frequency, its forced oscillations, and then the student measured the amplitude at different values of the frequency near the resonant frequency. So at the resonant frequency there will be a peak. The peak is at the resonant frequency. We have to determine the value of that. So the peak is somewhere over here. I'll consider this. So if I draw a straight line down, this is where we get our value. 10 units in the x-axis represents 10 boxes represents 0.2, so 0.2 by 10. Each small box is 0.02 hertz. So this is 1.42 hertz, 1.44, 1.46, 1.48, 1.50, 1.52 hertz. So our resonant frequency is 1.52 hertz. Now we have to determine the value of the mass. We know that the time period is 2 pi root over m by k. We also know that t is 1 by frequency, or frequency is 1 by t. This is the more generally known term, so we can just change the places. So t will become 1 by f. So 1 by frequency is twice pi root over, the mass is unknown, the value of k is given, the resonant frequency over here is 1.52 hertz. We can place that as well. So root over m by k is 1 divided by twice pi into 1.52. So squaring both sides, we get m by 30 equals to 4 pi square into 1.52 square by over under 1. So m will be 30 divided by 4 pi square into 1.52 square. If we calculate this, we'll get a mass of 0.329 kilograms. It would be better to give this value in 2SF. 3SF is overkill over here. Now we have to explain why our value of f0 may not have been accurate. Now if you look at the graph, there weren't a lot of points in between 1.4 and 1.6. So we didn't have any readings over here. So the graph may have also been like this. So something like this, or something like this. So the peak might have been anywhere over here somewhere. So if we had more readings in this region, we would be we could tell that this is the peak more reliably. So there are not enough readings around the peak or the maximum value, or between 1.4 hertz and 1.6 hertz. The position of the peak is uncertain. It could have been to the right or to the left. We don't know certain. Now in part C, the student suggested that a motion sensor and data logger arranged in this manner would improve the experiment. We have to explain how using them would improve the experiment. The data logger can take readings faster than a human can. So using that, we can take more readings per second when the mass is oscillating. So there will be less uncertainty when we measure the amplitude at a given frequency. So the quality of it being able to take readings faster than us is called that high sampling rate. So if low sampling rate means we can take readings slower, while high sampling rate is the vice versa. Now in question 2, we are given this apparatus for cooling hot water. Now the student used the hot plate, this hot plate over here, to heat the water until it boiled. Then he moved the glass beaker onto a heat-proof mat to allow the water to cool. We have to identify one safety issue with this. Since this beaker will be heated, the beaker might have a high temperature, so if we touch it we might get burns. So we should use insulated gloves or tongs to move the beaker. So we write that we use tongs to move it. Now in part B, the student suggested that the relationship between the temperature of the water and time is this expression over here. We have to devise a method to investigate the validity. Since we have a power over here, we'll take ln on both sides. So ln theta. Since this is a relationship between theta and t, we need to get t outside of the power, so we'll take ln on both sides. Doing so, we get ln theta naught plus ln e to the power minus bt. Ln e is 1, so we'll get ln theta equals to ln theta naught minus bt. So this is a if we rearrange this further, we get ln theta equals to minus bt plus ln theta naught. We can compare this to y equals to mx plus c. The gradient of the graph will be minus b. This is not the whole answer. The answer wants us to devise a method to do this. This is the graph we'll get after using our method. So we need to think about this. We'll keep this here. For this we need to measure theta and t. So we can measure the t time over here using a stopwatch. Now we'll measure the initial temperature of the water and then turn the mains powered hot plate on. So we start the stopwatch when we turn the main switch on. So we started just when the initial temperature is recorded. We do that simultaneously. Now we'll record the temperature at fixed time intervals. The time intervals. and we'll start it before every reading so that the solution becomes uniform. And we'll keep on doing this until the temperature of water is almost equal to the room temperature. Now we'll talk about the graph and in the last point. So now we have to plot a graph of it will have a y-intercept at ln theta naught. This is the y-intercept. So it won't be a straight line to origin, it will just be a straight line. Now on to question 3. We are given that a student investigated the force F between two bar magnets using the apparatus shown. So basically using this top pen balance and the change of mass when the bar magnets are separated at distance x. We have to describe an accurate method to measure the single value of x using a 30 centimeter ruler. So we'll place a ruler over here. We have to write down how to make it accurate. So one of the first points that should come to your mind is using a set square to ensure that it's vertical. So we'll clamp it. The distance we should record is from the bottom of the top magnet to the top of the bottom magnet. This is the distance we want to measure. So we state that. So we record this value. So this value will be something d1, this value will be d2. D2 minus d1 will be x. Instead of talking about subtracting this, you can also talk about the difference, record the difference between the positions. And we have to state another point about the precautions. And now we can talk about keeping the ruler close to the magnets or taking readings from eye level. Now the student predicted that the relationship between f and x will be f equals to kx to the power p, where k and p are constants. We have to explain how a graph of log f against log x can be used to determine the value of p. So if we take log on both sides, we'll get log f equals to log kx to the power p. We can write this as log f log k plus log x to the power p. Now we can bring the power down, so log f will be p log x plus log k. This is comparable to y equals to mx plus c. This is c, this is x, this is m, this is y. So p is the gradient over here. So p is the gradient of this graph. Now we are given the values of x, the distance, and the corresponding force F. We have to plot a graph of log f against log x, so we can put our values over here. So this is log f, this is log x. So if we calculate the value of log 11.22, we get 1.05. For this we get 0.88, 0.72, 0.54, 0.32 and 0.07. Now for log x, log 102 is 2.01, 117, 2.07, 2.11, 2.16, 2.22 and 2.29. Now we have to draw a graph of log f against log x in this grid. So log x is in the x-axis. Log x is from 2.01 to 2.29. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes to go from 2.29 to 2.01. This comes out to be 0.035. So we can take 0.05 for each box. We can start from 2.0 then. So 2.00, 2.05, 2.10, 2.15, 2.20, 2.25, 2.30. This is in log x in millimeters. Now for f, the highest value is 1.05, the lowest is 0.07. So we go from 0 to 1.05. So 1.05 minus 0, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 boxes. This comes out to be 0.09, so we can take 0.1 for each box in the y-axis. We choose the number slightly bigger than what we get, so we get 0.09. 0.1 is slightly bigger than that. We take a number that's slightly bigger than that and easily workable in a graph. So numbers like 0.1, 0.05, 1, 5, 10. It's easier to work with a number like this. So 0.33 or 0.09. It's easier to just switch to 0.1. Working with 0.09 would be a very big headache. So we can start here from 0. So 0.10, 20. And we should label this axis as well. This is log f in millinewtons. So log force in millinewtons. Now our first point over here is 2.01 in the x-axis and 1.05 in the y-axis. Each 10 box is 0.05, so each small box is 0.005. We need to go 2 of these boxes, so this is 2.01. 2.01 comma 1.05, so 1 in between 1 and 1.1. This is where we have our first value. Our second value is at 2.07 comma 0.88. This is 2.5, this is 2.6, this is 2.7. So this line on this line lies 2.07. Each 10 box in the x-axis, y-axis represents 0.1 units. So each small box is 0.01. So 1, 2, 3, 4, 5. This is 0.85, 86, 87, 88. That's our point. Our third pair of values is 2.11 comma 0.72. This is 2.10, this is 2.11, and we have 0.72. The next pair of values we have is 2.16, 0.54. 0.54 is over here, and 2.16 would be over here. Yeah. The next pair we have is 2.22, 0.32. 2.22 is over. So 2.22 is over here. And 0.32 is over here. So this is and our last set of values is 2.29, 0.07. This is 2.29 and 0.07 is this is 9, 8 and this is 7. Now we can draw a line of best fit from this. So if we try to draw the line of best fit, it's not quite there. So we are back with the line of best fit. Now in part 2 we have to determine the gradient of the graph. We can take 2 points on the graph over here. It cuts at 1 over here. 1 is easy to use. So we can use that triangle over here. The gradient from that triangle would be the difference in y value, so 1 minus 0. This value is 2.31, 0. This point over here is 0.30, 1.00. So 1.00 minus 0 divided by 2.03 minus 2.31. So the gradient would be minus 3.57. The gradient wouldn't have a unit since this is a graph of logarithms. Now we are told that the student suggested that the relationship between f and x is an inverse square relationship. We have to deduce if the graph supports that or not. The inverse square law states that the forces, so inverse square relationship suggests force proportional to 1 by x square, so basically x to the power minus 2. This is the value of the gradient. If our gradient was minus 2, this we could support this. However, the gradient we get is minus 3.6. So we cannot support this. Gradient of log f against log x graph should be -2. However, it is -3.57. So this suggestion is not supported by the graph. Now in question 4, we are told that a student made measurements of a circular convex lens as shown. The student used vernier calipers to measure the diameter. We have to explain one technique she should use. Now when we are talking about diameters, one of the most common techniques would be to check in different orientations, and a common method for vernier calipers and micrometer screw gauges would be to check zero error. And for diameter, a common point would be different orientations. You could talk about any one of them. If we do this, we reduce the random error. You could have had a question about 2 points. If it did, another point you could write about was the zero error. When we talk about random error, we talk about eliminating it. When we talk about random error, we talk about reducing it. When we talk about systematic error, we talk about eliminating it. Zero error is a systematic error because it's the same for every reading. Every reading is affected by the same amount if there is a zero error. So if there's a zero error of +3, every value will be 3 more than what it should have been. In random error, sometimes it's +1, sometimes it's -1, sometimes +2, sometimes +3. You have no idea of the errors individually. Now we are told in the next part that the student estimated that the thickness of the center of the lens was approximately 5 mm. We have to explain the most appropriate instrument that the students should use for a single measurement of t. So we are not using repeats. Since this is only 5 mm, we should do it with a micrometer screw gauge. And to justify it, to explain it, we have to calculate the percentage error. So using a micrometer screw gauge, so 0.05 by 5 into 100%, so 0.1%. Now in part B, we are told that the student placed the circular convex lens in a holder and set up an apparatus as shown over here. Now we're told that the student moved the position of the holder until the lens formed a sharp image, and then measured the distance u and v with a meter rule. So u is this distance over here, v is this distance. We are given the focal length is uv divided by u plus v. And we have to show that the uncertainty is in f is about 0.2 centimeters. When there's an addition or subtraction, we add the uncertainty directly, and when there's a division or multiplication, we add the percentage uncertainties. So uncertainty for u plus v, we have to find the uncertainty. So uncertainty in u plus v is equal to uncertainty in u plus uncertainty in v. So 0.1 plus 0.1, 0.2. So percentage uncertainty in that will be 0.2 divided by 29.6 plus 19.2 into 100%. This would be 0.41%. Now the percentage uncertainty in u would be 0.1 by 29.6 into 100%. This would be 0.34%, and percentage uncertainty in v would be 0.1 by 19.2 into 100%. This would be 0.52%. So percentage uncertainty in f is equal to 0.52 plus 0.34 plus 0.41, which comes out to be 1.3%. We want the uncertainty in f, not the percentage uncertainty. So uncertainty in f would be the percentage uncertainty, so 1.3 by 100 multiplied the value of f, which is 11.6. We'll get a value of 0.15 centimeters from here, which is about 0.2 centimeters. Now in part C, we are given the formula for refractive index is 1 plus d square by 8tf. We have to find the value of n in the first part. So 1 plus 5.02 square, 8 times 4. We have to convert this into centimeters, so 4.28 into 10 to the power minus 1 times 11.6. If we calculate this, we get a value of 1.63. Since all of our given values are in 3SF, We'll use 3SF for our answers in this questions. We have to determine the percentage uncertainty in the next part. The percentage uncertainty in n would be, since it's d squared, so twice the percentage uncertainty in d plus the percentage uncertainty in t plus the percentage uncertainty in f, since they are all in multiplication and division form. So percentage uncertainty in n is 2 times percentage uncertainty in d plus percentage uncertainty in t plus percentage uncertainty in f. So 2 into 0.02 divided by 5.02 plus 0.01 divided by 4.28 plus 0.2 by 11.6, everything multiplied by 100%. We'll get a value of this is the percentage uncertainty of this term over here, not the whole term, this term exclusively. So d square by 8df, d square by 8df percentage uncertainty in this will come out to be 2.8%. The percentage uncertainty in n will be 0.63 was the value. 0.63 was the value of this. So this value over here is 0.63. This value over here is 1, so 1.63. So 0.63 times 2.8 by 100. This is how much it could vary. And the value of n itself is 1.63. So we put that over here times 100. If we do that, we'll get 1.1%. Now in the last question, we are given that the refractive index is 1.52. We have to determine whether this lens could be made out of that. There are two methods for this. One is the range method. Another one is the percentage difference method. For the range method, we know that uncertainty over here for n is 1.1% and its value is 1.63. Since the value of crown glass is less, we'll find how much less this value of n could be due to the percentage uncertainty. So minimum n minimum for the thing we were experimenting with would be 1.63 minus 1.63 into 1.1 by 100, which would be 1.61. This is not in the range, so if the minimum refractive index is 1.61, 1.52 is even less than that, so this couldn't have been crown glass. So as or lower limit or now in the percentage difference, we have to find the percentage difference between our value, so 1.63 minus the wanted value 1.52. Since that is the 1.63 is an experimental value while 1.52 is a data book value, this will go on the denominator. The percentage difference will be 7.3%. Since the percentage difference is more than the uncertainty, this cannot be groundless. And this is it for this paper.